As the work done by a varying force is defined as a scalar quantity, the figure shows diagram shows a block is affected by a variable force that makes an angle theta with the displacement along the horizontal. And from the definition of the work, we got the work done by a varying force as the integral over f dot r as dot product of vectors, that is f cosine theta dr. As we said before, f dot dr is nothing more than the projection of the vector force on the displacement, that is f cosine theta, where the perpendicular component of the force does zero work. And in this case, as you know, f in the integrand represents the magnitude of the force, and dr, that's the magnitude of the object's displacement, and theta is the angle between the vector, force vector, and the displacement vector. To understand the work done by varying force, if you are given a graph of force versus position, where the force, as you can see with the red lines or the pink lines, varies the positions from this value to a larger value in here, then drop down to another value, and then drop to very much less than the previous ones. In this diagram, we can get the work done by this varying force by taking the area under the red or pink lines. That is the area of the rectangles. The sum of the area of the rectangles represents the work done by this force when this object is displaced from this position to this position. To better understand the idea of the work done by a varying force by using a graph, by taking the area under the curve, if the curve is a parabola like this, is changing in this way, what is the best way to get a good answer out of this? Well, as you can see, the idea of integral is nothing more. It started with the sum of the areas of these rectangles. Again, you can see there are some gaps in here, which shows that you may get not a good approximation when you're getting the area under the curve. So a better approximation is when the intervals of x, while the force is changing, these intervals as get smaller, they get smaller. You get a better approximation. As you see, you can see here the gaps between the rectangles, and the curve is very much reduced. And in this case, from here, the idea of integration actually comes from this relation. And this is a good approximation to get from this graph the area under the curve as the sum of all these rectangles, thin rectangles. In this example, a force is given in terms of unit vectors notation, and this force is changing as its x and y components shows, the changing with x and y. And as this force acts on the object, is going to displace it along the x-axis from a position at the origin to another position 5 meters away from the origin. Well, to get how can you get the work done by this force on the object? Well, to do that, of course, you have to follow this relation, and write delta r or dr as dx I hat plus dy j hat, as the object is moving only along the x-axis. Dy is equal to 0, so it turns out to be dr is nothing more than dx only, and this one gone. In this case, we can just substitute that into the integral, or taking the dot product of the vector with dxi, you're going to get 4x dx. In this case, the limit of integral is going to be reduced from r1 to r2 to that of x1 to x2, as you can see, because the only variable for the integrand in the integration is x. So our limits are from x1, that is equal 0, to x2, that is equal 5. If you just substitute the limits and carry out the integration, you're going to get the work done by this force as 50 joules. This is an example just to let you know how to get the work done by a varying force from a graph. If the graph of the component of force along the x-axis is given versus x, this means that this force is going to do a work on the particle as it affects the particle, as it acts on the particle, and it will displace it from x equals 0, for example, to x equal 8, and then also in B from x equal 8 to x equal 10, and in part C from x equals 0 to x equal 10. How can we do that? To do that, for the first part of the problem, if you want to get the work done from x equals 0 to x equal 8, this is simply you apply the relation, which is fx dx, and the limits from 0 to 8. As long as the graph is given, so it's simply, this is the work for this interval from x1 of a position to x2 for this displacement is simply the area under the curve of the blue triangle, which is half the base multiplied by the latitude, and the base is 8 and the latitude is 6 newtons. So 8 meters by 6 newtons, and then divided by 2, that is 24 joules work done in this displacement. For the second one, from position 8 to position 10, again we apply the same relation, where the area under the curve this time is the yellow triangle, and the area under the curve of the yellow triangle is also half the base, which is 10 minus 8, that's 2, and then multiply by minus 3, because here the force is opposite to the displacement, has a minus sign, as you can see here, by minus, and you get minus 3 joule. This means that this negative sign indicates there is a loss in energy as a result of the action of the force, because the force acts opposite to the displacement. So some of the motion has gone, or the motion of the particle has gone in this under the effect of this force. And finally, if you want to find the work from position x to position 10, simply all you can do, you have to add up the results in A and B, including the signs, obviously. Then you're going to get an answer of 21 joule. That is the answer for part C.